Binary tree insertion involves a process of comparing nodes as either less than or greater than, or of course equal to. At each comparison, if the node to be inserted is less than the node it's currently being compared to, the algorithm drops down a layer to the left child. And if the node's greater, it drops down to the right child. For an internal node in a tree to have only one child, all descendants of the node must be either all greater than or all less than the node. If we imagine the nodes to be inserted into an empty tree were stored in an array in order of insertion, if at every node in that array, all nodes further back in the array were either all less than or all greater than that node, a degenerate tree will form. So in looking at how insertion order or nodes affects the structure of a binary tree, for all the ways that this pattern occurs, a different binary tree can form. So in these little figures that I've drawn, we can see that this increases by a power of 2 each time the number of input values increases by 1. So the pattern for all values of n is for n, the number of degenerate trees that can be formed is 2 to the power of n minus 1. So the easiest way to think about this problem is that all surnames that meet the criteria of having the specified prefix are contained within the range from the surname immediately before the prefix and immediately after the prefix. The example I've given is for the surname with the prefix Smith, and the two bounds of the range are found by substituting the last letter for the letter prior, the G, and the letter following, which is I. And using these two prefixes as bounds, we can recursively search through the tree for all nodes between these bounds, with any node that falls into the range being added to the list of nodes to be returned. As described here in my report, balancing a binary search tree is best accomplished in a two-step process. The first utilises the in-order traversal method, since this visits the node in a sorted order. And while traversing the tree, the nodes can then be added to an array, which the resulting array, of course, is sorted. So then we can build the tree up again from the sorted array. This step is very intuitive and involves recursively splitting an array in two. At each recur, there are 3 nodes of importance. The middle node, where the array was split, becomes the root node, and the nodes that sit in the middle of each of the left and right halves are the left and right children of that node, respectively. So on and on it builds the tree from root to leaves, and this entire process takes linear time because both steps take linear time. They both access the nodes once, and therefore the entire algorithm to balance the tree takes linear time.